and write it as an integral with respect to y. So this is the same as the integral with respect to y. Then we have t for the outer integral. Bless you. dp dy. By the way, the only reason I'm using this particular chalk is because it's coming up on Easter. It's not writing as smoothly as I'd like. All right. From g1 of t to g2 of t. So now we've written this line integral as a double integral over the entire region, because x, which is, we're calling it t here, but x and t are the same in this case. X is going from a to b, y is going from g1 of x to g2 of x. We're covering the entire region D. So what we have is minus the double integral over the region D of dp dy, dA.
Where did the negative sign up front come from?
Oh, because here I have g1
Right.
minus g2,
All right.
but I wanted to list g2 first.
Okay. So
Yeah, so I just minused everything.
So you can call like from A to B and from G1 to G2, call all of that D.
Yeah, because I erased it, but that's the definition of one of the first definition, type 1 definition of D that I put down. That's exactly these limits: x from here to here, y from here to here. So now we have this as a double integral, which may be easier to evaluate than the original line integral that you had. Okay. All right, so it took viewing this region as a type 1 region, seeing that dx is 0 for these two pieces so we forget about them, and then taking these evaluations of p at the upper and lower limits in y and rewriting it as an integral of a derivative with respect to y. So we end up with this double integral over the region. So any questions about how we got from the original line integral all the way to that? So a bit of reverse engineering, if you will. All right. Now, using a similar approach and the type 2 definition of a region, what you would find, you know what, I should have left this up. I'll put it, okay. Well, maybe not everything, but at least pieces, because the orientation is going to be important. All right, so this is type 1. Whereas if we view the region as something of type 2, now granted we're drawing different regions, but just to show what type 2 looks like. So this is y running from C to D, x going from H1 to H2. All right, so these are limits on x. So what you would find, we still have the same orientation, counterclockwise. Right. What you find is that the line integral of q dy over the entire curve is equal to the double integral over the region of dq dx. So here we have the line integral of p dx. You're differentiating with respect to the opposite variable and you're integrating over a region. Here we have a minus sign. Here, q dy, we're differentiating it with respect to the opposite variable. We get dq dx, again integrating over a region, but here in this case it's a plus sign. Okay.
What's the like the actual difference? Like what is minus that whole difference?
Okay, so one difference that we could see between the two situations is this, that because we're using the same orientation all the way around, but all right. I was actually anticipating his question, and I looked at the pictures like, oh yeah, that's why, and I was ready to give this explanation, and of course I've forgotten it.
Yeah.
But anyway, because you have to look at where you have the lesser or greater x coordinate or y coordinate, and what sign it's going to get in the in the integral. So, so what we have here is, here we have the because here we have the lesser y coordinate to the greater y coordinate. Here we have a lesser x coordinate to the greater one. And you know what? I think in order to satisfactorily answer this question, probably the only thing that I can do is not be lazy and actually work it out for you right now.
It'll be okay. Curiosity just doesn't have that
Yeah.
much of a drive.
Yeah. Okay. So. Yeah. All right. So. Yeah, but so what's happening here is, for instance, if we let's do a contrast. H2 of t over here, G2 of x over here. Notice, okay, actually now I can answer your question.
Okay.
Now I remember.
All right.
As we trace through a curve along a proper orientation, we're going from the lesser y coordinate to the greater. Here, as we trace the upper limit in x, using a proper orientation, we're going backwards in x, from the greater x coordinate to the lesser x coordinate. So there's an asymmetry there.
Okay.
Yeah, and that's why you end up getting opposite signs. Okay. Which, yeah, you would see if you worked it all out.
Yeah.
Okay. So now we can put this and this together, and we get Green's theorem, which says that the integral over a simple closed curve of positive orientation of this line integral p dx plus q dy is equal to the double integral over the region it encloses of dq dx minus dp dy. Yeah. So, if you have any given line integral over a closed curve that satisfies the other assumptions, you can try rewriting it as this by carrying out the differentiation and seeing if that's easier to evaluate. Or, give it a double integral over some region that might be difficult to evaluate. If you find a functions p and q so that this expression is equal to your integrand, then you might find it easier to go the other way, from the double integral to the line integral over its boundary. So, whichever situation you're in, you can switch to the other and see which is more practical. Okay. All right. Now, the thing is, this has only been shown for a very simple type of region, one that can be looked at as both type 1 and type 2, which doesn't really allow a whole lot of regions. Basically something that's either triangular or something that is a triangle with curved boundaries. It's a bit restrictive. But once you have this for those simple kinds of regions, it's actually not very hard to generalize it to other regions. So I'll draw some pictures and show you what I mean by that. So I'm going to draw two regions that could be, each one of them can be viewed as either type 1 or type 2. This and this. Called D1, D2. And, okay, where are my colors? Okay, so this curve, so the entire boundary of D1 except for the shared boundary.